right, geometry people, we're looking at our samples for 11.4b. We'll start with looking at a number line and finding a probability of picking a point on a particular segment based on conditions. So let's see, on sample 1, what is the probability of randomly choosing a point on line segment PQ from here to here, if it is equally likely that you will choose any point on RT from here to here? And then express your answer in fraction, decimal, and percent form. This will be the only problem that we're going to do all three of those forms just to make sure that we are familiar with going back and forth between those different forms. Well, what's the probability here of choosing a point on line segment PQ? Well, let's figure out how long PQ is. To figure out how long PQ is, to see how much space we have to pick a point where we want, we would find the absolute value of the difference between these two numbers, subtract them in either order, take their absolute value. So I'll subtract 0 minus negative 2. And that gives me 2, and the absolute value of 2 is 2. I could equally correctly subtract the other way. As long as I take the absolute value, I'm going to get 2 either way. So if I did negative 2 minus 0 and took the absolute value of negative 2, which is 2, I'd still end up with the line segment being 2 units long. All right, so we are putting our favorable outcomes on the top. So there's two spaces on this number line where we can land where we want to land. And then how many spaces could we land on? Well, anywhere between R and T. Let's see how long it is. Find the difference and take the absolute value. 2 minus negative 3. 2 minus negative 3 gives you 5. The absolute value of 5 is 5. So there's 2 spaces to get what we want out of 5 spaces where we could land. So that gives us 2/5 of a chance of randomly picking a point and landing on line segment PQ. 2/5 is the same thing as 4/10, and we can write 4/10 as 0.4. And 4/10 is the same thing as 40 over 100, so that gives us 40%. Is another way to express our chances of landing where we want. All right, now we'll move into problems where we have areas that we want to choose or land in, and what are the chances of us actually landing in those areas. Sample 2, what is the probability of landing in the small circle that we have colored in yellow if it is equally likely that you will land anywhere in the large circle? So we're going to land somewhere in the circle. We actually want to get here. What are our chances if we could actually randomly land anywhere possibly on that circle? What are the chances that we would actually land in this small area? Well, again, favorable outcomes on the top. The area of this small circle would be pi r squared. And our radius is 1.5. I determined that because they gave us the diameter 3, so I cut that in half to get my radius of 1.5. So pi times 1.5 squared is the area of the circle where I want to land. The big circle here, they give us a diameter of 10, so the radius will be 5. So the area of the large circle that includes every point inside of the circle, this larger circle, including the smaller circle itself. So that would be pi times 5 squared, pi times the radius squared for the big circle. And then I set about simplifying that. So the pi's are going to cancel out. That's nice. The 1.5 squared is 2.25, and I can do that mentally because I know 15 times 15 is 225, and I just put my decimal point in 2 places for the 2 decimal places in my product. And then on the bottom 5 squared is 25. So I'm going to go ahead and move my decimal point twice to the right in both numbers, in the numerator and the denominator. That's multiplying by 100 over 100. That gives me 225 over 2500. And then I'm going to divide both of these by 25. There are 9 25s in 225, and there are 100 25s in 2500. So that gives me the chances of landing in that small circle, only 9 out of 100 possibilities. So not a great chance that I'm going to land where I want to. Sample 3. This picture is kind of like the last one where we have a desired region where we want to land or find a particular point. It's possible to land anywhere or randomly choose a point anywhere in the big rectangle, but we want to choose a point where it is yellow. So what is the probability of randomly choosing a point in the shaded region if it is equally likely you will choose any point in the rectangle? So what's the probability of choosing a point in the yellow region? So again, we're going to find the area of where we want to choose a point, and that's a triangle. So 1/2 base times height. The base is 6. It's a right triangle, so I can use the legs for the base and the height. The height would be 4, because this is 4. So 4, 4. So 1/2 times 6 times 4 is 1/2 base times height of the triangle. Those are our favorable outcomes, the triangle area, over the area of the entire rectangle. That would be length times width. So 3 plus 6 for the length times 4 for the width. So 3 plus 6 times 4. Now I'll simplify that. Half of 6 times 4 is half of 24. Half of 24 is 12. Here we'll have 3 plus 6 is 9 times 4. 9 times 4 is 36. So 12 over 36 reduces down to 1/3. So there's a third of a chance that you would randomly pick a point that would happen to be in the triangle area if you were definitely restricted to choosing a point somewhere within that rectangle. All right, so that's all for our samples. It's time to move on to your quiz for this lesson and then move on to your next lesson. We'll see you next time.